Welcome. This is the video for section 6.3 on fractions and specifically related to multiplication and division. So right before the break, we talked about fractions more generally. So far in this course, we'd only been talking about whole numbers. And so my plan is to just talk through this section of the notes that's on multiplication and division. We ended up doing a lot of examples on addition and subtraction in the last class where we met, so I want to talk through multiplication and division in a little bit more detail and do some examples here. So that's my plan, is to basically work through these notes and do more examples related to multiplication and division. Okay, so as far as models go, we did talk about multiplication last time, but I'll just kind of review. As far as models go, for whole numbers, we can think of multiplication as repeated addition, and this also works well for when we have a whole number times a fraction, as well as a fraction times a whole number, because commutativity of multiplication tells me that it doesn't matter which order I do the multiplication in. And so, for instance, if I have, like in this example, 3 times 1/4, then what I'm going to do is I'm going to think about adding this distance of 1/4 3 times, and that gives me 3/4. Okay. The model is a little bit more complicated, or this idea of thinking of multiplication as repeated addition breaks down when we think about multiplying two fractions. So for example, 1/3 times 4/5. So we can think of what 1/3 times 4/5 means, and it means 1/3 of 4/5. So here I have an example of what 4/5 of this rectangular area looks like. And basically what I want to do then, if I want to represent 1/3 times 4/5, is I'm going to break this region of 4/5 into thirds, which I'm not doing particularly evenly, but I think we hopefully get the idea. I'm going to break this region into thirds, and let's do it. Just trying to make it a little bit even here. Well, you get the idea. So I'm going to take 1/3 of this region of 4/5. And so 1/3 times 4/5 should be what we have represented here. So if I think of this in regards to what we have represented here in the purple. So if I'm thinking of this in regards to this whole the whole original rectangle, what that is, if I count, it's 1, 2, 3, 4, 5 by 1, 2, 3. So it's out of 12. Oops, sorry, 15, right? There are 15 boxes here. And we've colored 1, 2, 3, 4 of them, right? So 1/3 times 4/5 should be 4/15. Great. So that's what one way we can model this fraction multiplication when we have two fractions. And for writing a rule for how multiplication of fractions works, well, it looks like if I take a over b times c over d, I'm just going to multiply the numerators and multiply the denominators. Okay, and so let's look at a couple of examples just to make sure that everything is clear. And so here, if I have 2/3 times 3/13, I'm just going to multiply 2/3 times 5/13. I'm just going to multiply my numerators and multiply by denominators. So 2 times 5 is 10, and 3 times 13 is, I think, 39. And then, of course, I can ask myself if this fraction can be reduced, and it looks like the answer is no to me. I realize, or simplified, I guess, is the book that the word that your book prefers to use. And I can see that because 10 is only divisible by 2 and 5, and 39 is not divisible by either 2 or 5. Okay, so similar example with 3/4 times 28/15. I am just going to multiply 3 times 28, and that's 84. And then I'm going to multiply 4 times 15, which is 60. So here I have 84/60ths. Again, this is written as a mixed number. Or sorry, this is written as an improper fraction, right? Because the numerator is larger than the denominator. But you might also notice that this fraction can be simplified or reduced. And I see this because both of them are at least divisible by 2. And in fact, they might both be divisible by 4. I think they're both divisible by 4. Let's see, is 84 divisible by 4? Yeah, it looks like that's 21 times 4. And 60 is divisible by 4. That's in fact how we got it, right? It's 4 times 15. And I can reduce this even a little bit further because I see that 21 is divisible by 3, and 15 is also divisible by 3, so I think this is 7/5. But stop me if I made a mistake here, and by stop me, I mean feel free to comment or shoot me an email if you see any mistakes, right? So here we have, again, an improper fraction because the numerator is bigger than the denominator. We didn't expect it to not be an improper fraction. We're just simplifying. But if I wanted to write it as a mixed number, I see that 5 goes into 7 just one time, and I have a remainder of 2/5. So as an improper fraction, or sorry, as a mixed number, I would write it as 1 2/5. Okay. So notice that when I'm doing this multiplication, what I did in my very first step was I just multiplied the numerators and multiplied the denominators. What I could have done instead is I could have noticed, and you might have noticed this as you were looking at this example, I could have said, notice that there were common factors in the fractions to begin with. So my first fraction is just 3/4 here. But if I look at 28 and I divide it by like 7, I see that that's 4 times 7. And I see that 15 is really just 3 times 5. And so if I were going to multiply these two fractions out, if I'm just looking at their common factors, I see here it's really easy for me to tell that these, what cancels and what my simplest form of this fraction is, which is 7/5. Really, there's no difference in these two methods. One is just writing out factorization in the second method, and the other one is actually multiplying large numbers out first, and then all right, for this last example, number 3 here, we're going to look at multiplying two mixed numbers. And in this form, we have this kind of like parentheses we can imagine sitting here, just so this is really clear. Sometimes they don't write those, but this is what this kind of would look like. There's these imaginary parentheses sitting here. Okay, so there are kind of two ways to multiply these mixed numbers. The first way is to turn them into improper fractions and then multiply, just as we did before, multiplying in the numerators and multiplying in the denominators. And so this is probably the most natural way to compute this product. So let's start there. So the first number is 2 1/3. So 2 is really 6/3. So this is really 7/3. And we're going to multiply that by 7 2/5. And 7 is 35/5. So this should be 37/5. And now, of course, these parentheses don't particularly matter. I just wanted to make sure the notation was clear. Okay, so now we're in the case where we can just go ahead and multiply numerators and multiply denominators. So multiplying 7 times 37 is 259, and multiplying 3 times 5 is 15. Okay, so now we can ask ourselves how many times 15 goes into 259, and that should be a bunch of times. Let's see, I think it's like 17 times. And my remainder then would be, let's see, 17 times 15 is 255, so my remainder should be 4 over 15. Of course, if I don't specify, then I don't particularly care which form you leave your answer in. If you wanted to leave it as the improper fraction here, that's totally fine. But if it's given to us in a mixed number, it's kind of nice to give our answer in the mixed number too. And you should definitely be able to go back and forth and use either notation, I guess. Okay, so this is one easy way to do this product is to turn these two mixed numbers into improper fractions first. But another way to do it is that we could instead actually multiply these things as mixed numbers. So this is maybe the less intuitive way to do this, but I think it's a good investigation into kind of the properties of multiplication, as well as kind of recalling what these mixed numbers mean. So remember, 2 and a third really means like 2 plus a third, and 7 and 2/5 really means 7 plus 2/5. So I'm going to kind of rewrite these in terms of addition. And now that I have these binomials, if I want to compute this, one thing I can do is I can kind of think of this two ways. I can FOIL or I can distribute. But either way, I have to kind of make sure I'm multiplying out this product kind of completely, right? So here I might take all of this 2 plus 1/3 and distribute it to the 7 and distribute it to the 2/5. So when I do that, I get 2 plus 1/3 times 7, and I get 2 plus 1/3 times 2/5. Okay, so now I want to distribute the 7 to each of these terms and the 2/5 to each of these terms. All right, so just distributing twice here just to make sure I multiply these things properly. So 7 times 2, that's just 14. And then this is really 1/3 times 7 over 1. And this is really 2 over 1 times 2 over 5. And 2/5 times 1/3 is 2/15. And then let's simplify this a little bit. So I have 14 plus 7 over 3 plus 4 over 5 plus 2 over 15. And now let's go ahead and take these three fractions and let's get a common denominator and combine these three fractions. So it looks like my common denominator here will be 15. So this 7 over 3 I'm going to multiply by 5 over 5. So that's 35 over 15. And 4 over 5 I'm going to multiply by 3 over 3. So that's 12 over 15. And I'll just leave my 2/15 the same. Okay, so now I have 14 plus 35 plus 12 plus 2. So that's 49 over 15. So now I can see I kind of have this weird like 14 and an improper fraction. So I'm just going to turn that improper fraction 49 over 15 into a mixed number. And I see 15 goes into 49 3 times. So this is 14 plus 3, and I'm left with 4 over 15. And of course, really this just means, this 3 and 14ths really just means 3 plus 4 15ths. So this is really 17 and 4 fifteenths, however you want to write it. Okay, it's 14 plus 3 plus 4 fifteenths, which is exactly what we had before, right? So no surprise there. So that's always good news, right? These are the same answer. Just done two different ways. So the first way we computed this product was by turning those improper fractions, or sorry, those mixed numbers into improper fractions. The second way we actually dealt with them as mixed numbers. So we had to kind of employ rules about distribution or distributing things and kind of really think about what those mixed numbers meant in order to do that multiplication properly. If I don't specify, it absolutely doesn't matter which way you do this, but I would be kind of comfortable at least kind of understanding this second method, kind of what's happening here and why these rules work. We should obviously get the same thing, but yeah, if I don't specify, of course, you can compute it either way. And you probably think finding the improper fractions is the easier way to go, and I would agree. But it's good to make sure that we do understand how these mixed numbers are working. Okay, great. So to summarize some of the concepts involving multiplication. So again, we have closure under the set of the set of fractions under multiplication. So just like we had for whole numbers, if I took two whole numbers and I multiplied them, I got a whole number. Same thing happens under the set of fractions. So if I multiply two fractions, I get another fraction. And here we've been really talking about positive fractions. So if I take two positive fractions and I multiply them, I get a positive fraction. So that's hopefully not surprising. This multiplication is still commutative, right? So if I take two fractions, a over b, and I multiply c over d, it's the same thing as saying c over d times a over b. It's also associative. So this tells me that I can group things in any particular order, and that's fine. So this is telling me kind of about where the parentheses are placed if I'm only talking about multiplication. And there is also a multiplicative identity, which is just 1. So this tells me that 1 times any fraction is just that fraction, right? So 1 is still my multiplicative identity. And 1 is in the set of fractions. It's just 1 over 1, or actually any number over itself, as long as that number is not 0. Lastly, what we do have here that we did not have before was a multiplicative inverse. So this is where things change a little bit. And the multiplicative inverse says that for any non-zero fraction, a over b, there is a unique fraction. In fact, we know what it looks like. It has this form b over a, so that if I multiply a over b times b over a, or even if I do it the opposite order, right, b over a times a over b, I should get the identity, the multiplicative identity, or 1. Okay, so this is what the multiplicative inverse says. So we haven't really talked about inverses very much in this class because we didn't have multiplicative inverses until this point because we didn't talk about fractions, right? When I was talking about whole numbers like 3 didn't have an inverse in the set of whole numbers. We can see that the multiplicative inverse of 3 is 1/3, and that's in the set of fractions, right? So this is, now that we're introducing fractions, we can talk about this multiplicative inverse. And one thing that this is really useful for, and will come up down and build a foundation for later for students, is in talking about solving equations. So for example, if I have the equation 3/7x is equal to 5/8, the way that I solve this is by multiplying both sides by the multiplicative inverse of 3/7. So the multiplicative inverse of 3/7 is 7/3. And so that's what I'm going to do, is I'm going to multiply both sides by 7 over 3, right? So if I multiply both sides by the same thing here, which is what I'm doing, right, this 7 over 3, then I don't change the value of the equation. And so everything is fine, right? And I notice what this multiplicative inverse says is it says that on the left side here, since I'm multiplying 7/3 times 3/7, this is just 1 times x. And this is 35 over 24. And I don't think we can reduce this at all. No, looks good. Okay, or in other words, x is equal to 35/24, right? So this gives me a way to solve, or a method for solving algebraic equations, right? So, thinking of the multiplicative inverse just being the reciprocal maybe seems a little silly and unmotivated, but it does come up a lot down the line. And in fact, inverses are a kind of thing that are going to show up basically forever for as long as you can keep going in your mathematical career. So learning about them early is a really useful thing. So when students start talking about solving algebraic equations, it's helpful. When we start thinking about functions, they're very helpful, all the way through calculus and even far beyond. Inverses are going to be a very important notion. So it's nice to really think through using this language early and make sure you're using it correctly, obviously. So an inverse is basically something that undoes the operation to get you back to the identity. Okay, and of course, I guess we should mention that the multiplication is still has this distributive property. Okay, so that summarizes multiplication. There's not